Welcome to this video on probing Schrödinger's cat with neutron and cosmic radiation. We explore a novel approach to quantum measurement via phase-encoded scattering. The paradox of macroscopic superposition, exemplified by Schrödinger's cat, highlights the conflict between quantum states and classical outcomes. The setup involves entanglement, where a radioactive decay event decides the cat's fate. Until observation, standard theory suggests the cat exists in a superposition of alive and dead states. The measurement problem asks where the quantum realm becomes classical. The Schrödinger equation describes deterministic linear evolution, but measurement causes a nonlinear collapse to a single outcome. The question remains, what mechanism selects that single outcome? The dominant interpretations are the Copenhagen interpretation, where measurement causes a probabilistic collapse of the wave function, and the many worlds interpretation, where the universe branches into non-interacting realities for each possible outcome. Alternative frameworks include decoherence, where environmental interaction suppresses interference. Objective collapse suggests physical thresholds induce spontaneous collapse. Cubism views the wave function as a user's manual for belief, not a physical reality. The goal is non-destructive observation to peak without collapsing the state. Direct interaction, like the photoelectric effect proposal, risks destroying the coherence. We need a weak measurement approach to encode information without forcing an immediate state reduction. Our innovation is phase-encoded neutron scattering. We use a low-energy coherent neutron or cosmic particle as a probe. It weakly interacts with the cat's potential field, acquiring a phase shift based on the internal mass distribution, which is then measured by an interferometer. The interaction entangles the probe with the system. If the cat is alive, the neutron acquires phase shift A. If dead, phase shift D. The exiting neutron carries a superposition of both phase shifts, acting as a carrier of the system's quantum information. Scattering mathematics decodes reality. The probability of detection p theta includes a classical probability sum and a critical interference term. If the phase difference, delta phi, is non-zero, an interference pattern emerges, confirming quantum superposition. In the experimental design, we replace the cat with a macroscopic quantum system, a qubit, to mimic the alive and dead states. We measure the angular distribution of scattered neutrons to distinguish between a quantum superposition and a collapsed state. The signature of superposition is the interference pattern, confirming quantum coherence is preserved. The absence of fringes results in a flat classical summation, indicating a collapsed, decohered state. From a scientific perspective, dead is a shift from low-entropy organization to high-entropy disorder. This experiment detects this shift in organizational complexity via the scattering potential. Quantum coherence dissolves into the environment during this transition. The broader implications span quantum computing for non-demolition measurement of qubits, cosmology for analyzing CMB phase shifts, and metaphysics, offering a path to resolve the paradox without invoking a conscious observer. In conclusion, this approach provides a unified platform integrating scattering theory, decoherence, and weak measurement. We have a derived formula to predict observable interference patterns. Schrödinger's cat is no longer just a thought experiment. It is an empirical frontier ready for testing. Thank you. Here are the references and acknowledgments for the primary manuscript and key citations that frame this research.